So in yesterday's lesson, you revised the concept of linear sequences. Let's take a quick look at an example of one. So we have 8, 13, 18, 23 and 28. Now, how do we know this is a linear sequence? Let's look at the differences between the terms. We can see that the differences are consistent or constant, and they're all 5. So the fact that the first differences are all equal tells us that this is a linear sequence. Also, in your previous lesson, you looked at how to find the nth term of a linear sequence. Now, because the terms in this particular sequence have gaps of 5 between them, this means that this sequence is based on the 5 times table. So we can set out a simple table. If n represents the term number, we've got a first term, a second term, a third term, a fourth term, and a fifth term. And our terms are 8, 13, 18, 23, and 28. If we write out the terms for the 5 times table, just here, they would look like this: 5, 10, 15, 20, and 25. Let's think about the nth term. The nth term for the 5 times table can be expressed as 5n. But of course, we don't want the 5 times table, we want an adjusted version of the 5 times table. And if you look carefully, you can see that our sequence is 3 more than the corresponding term in the 5 times table. So the nth term for our sequence is 5n plus 3. See if you can find the nth term for this linear sequence: 7, 11, 15, 19, and 23. Let's look at the gaps between the terms. There's a gap of 4, or a difference of 4, which is consistent, which tells us we're looking at the 4 times table, which means the nth term will begin 4n. And if we simply write out the 4 times table, 4, 8, 12, etc., we can see that the adjustment is a plus 3 in this case again. Let's look at one final example. 10, 6, 2, -2, -6. We can see the difference between terms is -4, which means this time the sequence is based on the -4 times table, which means that the nth term will start -4n. Let's write out what the sequence of terms belonging to the -4 times table would look like. -4, -8, -12, -16, -20. And of course, we then need to look at the adjustment that would be required to create our sequence. So from -4 to make 10, we need to add 14. From -8 to make 6, we need to add 14. So our nth term has the expression -4n plus 14, or 14 take away 4n. Linear sequences are also sometimes called arithmetic sequences. So you can use these two terms interchangeably. Now let's have a look at a different sequence. Here are the terms: 6, 11, 18, and 27. I'm going to refer to these as T with a little subscript n, which means term. So for instance, T1 means term 1. And just above that, I'm going to fill in the n values. So n equals 1 corresponds to the first term, n equals 2 the second term, n equals 3 the third term, and n equals 4 the fourth term. So if I want to, for instance, refer to the fourth term, I would write t with a little 4 subscript, which equals 27. Now, let's have a look at the differences between the terms. 6 to 11, that's a difference of 5. 11 to 18, that is a difference of 7. 18 to 27, that is a difference of 9. So what we notice is that the first layer of differences are not the same. Now, what this instantly tells us is that the sequence is not linear. So, we then investigate the second layer of differences. 5 to 7, there's a difference of 2. 7 to 9, there's a difference of 2. So it looks like the second layer of differences are the same. And this tells us the sequence is what we call quadratic. And you've come across the idea of quadratic expressions before when we learnt about expanding double brackets. So because the sequence is quadratic, the nth term will have the format an squared plus bn plus c. And our job is to find out what numbers a, b and c are in this expression. So you've come across previously linear expressions for nth terms of sequences, and if we just had this part with the bn plus c, for example, nth terms like 3n plus 2, 5n plus 3, 7n minus 1, that's what you've come across previously. A quadratic sequence has an added element to it with a square term like this. So how do we find out the values of a, b and c? There are several methods for doing this. We are going to have a look at one specific method in this lesson, and then in a later lesson we will have a look at some of the other methods, and ultimately you will find and decide which method you like the best, which method you understand the most, which method you find the most efficient to use. So we're going to start off by finding the value of a. And we will talk more about where this result comes from a little bit later on, but a is equal to half of the second differences. So in this case, a is equal to a half of 2, because we can see very, very clearly that the second differences are equal to 2. A is equal to a half of this value, which is 1. So our nth term will be 1n squared plus bn plus c. And of course, we still have to find the values of b and c. So to find b and c, I'm going to set up a short table. N references the term number, so we have a first term, a second term, a third term and a fourth term in this example. Tn references the actual value of the term, so our terms are 6, 11, 18 and 27. I then include another row which refers to n squared. So let's find out the values of n squared. If n equals 1, n squared is 1. If n equals 2, n squared is 4. N equals 3, n squared is 9. N equals 4, n squared is 16. I then create another row, which is the term take away the value of n squared. So 6 take away 1 is 5, 11 take away 4 is 7, 18 take away 9 is 9, and 27 take away 16 is 11. And we find out, if we've done this correctly and if this is a true quadratic sequence, that we generate another sequence, 5, 7, 9 and 11. And this, we can see very clearly, is linear, because there is a very simple difference, which is consistent, of 2 between the terms. Now, can we find the nth term for this sequence? Yes, we can. We know it's based on the 2 times table, so it starts off with a 2n. 2 times 1 is equal to 2. 2 times 2 is equal to 4. 2 times 3 is equal to 6. 2 times 4 is equal to 8, using these n values up here. And we can see that the adjustment that we have to make very, very quickly is plus 3. So the nth term for this part is 2n plus 3, which tells us that b is equal to 2 and c is equal to 3, which tells us that the overall nth term, if you remember, it had the format an squared plus bn plus c, is going to be n squared plus 2n plus 3. I'm not going to write 1n squared. You can do if you want to, but there's no real need to do this. Let's check this. So we have just found that the nth term is calculated using this result, n squared plus 2n plus 3. So let's allow n to equal 1. And this tells us that the first term, if we use this formula, can be calculated by 1 squared plus 2 times 1 plus 3. And if we work that out, this comes to a value of 6, which is correct, because remember the sequence is 6, 11, 18, 27. Let's try another one. Let's work out what happens when n is equal to 3. This should give us the third term. So n is 3, so 3 squared plus 2 multiplied by 3 plus 3. So that's 9 plus 6 plus 3, which is 18, which is correct. So it does appear to have worked. So we're going to now look at another example. Here's our sequence of terms. So our values of Tn are 1, 10, 23, 40, and this time we have a fifth term, 61. So we have a first term, a second term, a third term, a fourth term, and a fifth term. Let's have a look at the differences between the terms. Plus 9, plus 13, plus 17, plus 21. So we can instantly see that the first differences are different. They're not the same. So this tells us it's not a linear sequence, it must be quadratic. Let's investigate the second layer of differences. Plus 4, plus 4, plus 4. So we can see very clearly that the second differences are the same. And it's this that tells us that we are dealing with a quadratic sequence. And as soon as we know it's quadratic, we know that the nth term will take the format an squared plus bn plus c. And our value of a is going to equal half of the second difference, which we've worked out over here. So that's half of 4, which is equal to 2. So far we know that Tn, which is our formula for the nth term, will equal 2n squared plus bn plus c. And like we did previously, we're now going to try and find the values of b and c using the same method. So let's set up a table like we did last time with the same references. I want to know which term I'm talking about. So I list values of n. I then list the values of the terms in my sequence, which are 1, 10, 23, 40, and 61. The next row of my table is not n squared, because in the formula for the nth term, we know that the formula begins 2n squared plus bn plus c. So we, in our table, have 2n squared. Now remember your rules of BIDMAS, your order of operations. This is 2 multiplied by n squared. So make sure that you square n first, then multiply by 2. Think about order of operations. Indices, which includes squaring, comes before multiplication. So let's work out the values of 2 lots of n squared. So 1 squared is 1, 2 lots of that is 2, 2 squared is 4, multiplied by 2 is 8, 3 squared is 9, multiplied by 2 is 18, 4 squared is 16, multiplied by 2 is 32, and 5 squared is 25, multiplied by 2 is 50. And we're then going to have the row, which is Tn take away 2n squared. So we need to do a subtraction, like this. 1 take away 2, negative 1, 10 take away 8, 2, 23 take away 18, 5, 40 take away 32 is 8, 61 take away 50 is 11. Now, the moment of truth, do we have a linear sequence? Well, we can see that the differences between these numbers is consistently 3, so this part is indeed, as we expected, linear. Let's make sure we can find the nth term for this part. The differences are 3, so it's based on 3n. If we do 3 times 1, we get a value of 3. We need to adjust it to make a value of negative 1, so it's going to be 3n take away 4. Let's check that. 3 times 2 is equal to 6, and yes, we adjust it to 2 by subtracting 4. So this tells us that Tn, the overall nth term for the whole quadratic sequence, is going to be 2n squared, which we found out previously, and then we'll include this part, which is 3n minus 4. Now, you may be wondering why, and we will talk about that in a little bit more detail later on. For the moment, we're just going to become really efficient at finding the nth term, and then we will discuss in more detail why this method, and other methods as well, can be used to find the nth term of a quadratic sequence. So we have one last example which you are going to try yourselves. The answers will come up as well, so pause the video, have a go, and then check your answer. So the terms of your sequence are negative 3, 2, 13, 30, and 53. Can you find the nth term of this sequence, an expression for the nth term of this sequence? So let's have a look at the answer to this. I'm going to set my table up as previously. So I have n, which is 1, 2, 3, 4, and 5. Then I'm going to fill in my terms, which are negative 3, 2, 13, 30, and 53. Let's have a look at the differences. So my first layer of differences, plus 5, plus 11, plus 17, plus 23. We can see these are not the same. It's definitely not a linear sequence. My second layer of differences, however, we can see that these are constant. So we know we have a quadratic sequence. So our nth term is going to take the format an squared plus bn plus c. And we also know that a is going to equal half of this second difference, which is 3. So we have 3n squared plus bn plus c, and it remains for us to find the values of b and c. So let's have a look at this a little bit more closely. So I'm going to set up again n, 1, 2, 3, 4 and 5, tn, negative 3, 2, 13, 30 and 53. And then this time we want to set up 3n squared. So again, remember we want to square each value of n and then multiply by 3. So we have 3, we have 12, we have 27, we have 48, and we have 75. Then let's do the subtraction. So we want to know what the numbers for tn take away 3n squared are. So subtract. So we get negative 6, negative 10, negative 14, negative 18, and negative 22. So now let's look at the differences between these terms. We can see it's consistently negative 4, which means that we are looking for these values to have an nth term which begins negative 4n. So let's check. Negative 4 multiplied by an n value of 1 is negative 4. But we want to make sure that we get to a value of negative 6. So how do we adjust? We subtract 2. Let's check. Negative 4 multiplied by 2 is negative 8. But we want to get to negative 10. Yes, subtracting 2 works. So this tells us that our overall nth term for our quadratic sequence, this sequence up here, is going to be 3n squared minus 4n minus 2. And as I said previously, we will find out in a little bit more detail later on why do we do steps like halving the second difference to get the value of a. For the moment, we're going to make sure that we can practice using this method efficiently.